Good morning. We are participating in the 152nd annual meeting of the National Academy of Sciences. Welcome. Tomorrow we will do a total on how many people are registered at the business session and give you that number. On Saturday, we welcomed the new members who had been elected in 2014, along with our foreign associates, of course, and I thought the presentation ceremony was equal parts fun and also great impressions over the achievements for which these new members are being honored and how they were elected. So it was a good event. Earlier in the day, we heard presentations from 6 of the new members, representative scientists, about some of their achievements, some of their discoveries, and what the prospects are in their various fields. It was very exciting, an unusually good group of speakers, I must say. Then yesterday we began scientific sessions with, I think, a lot of anticipation for good sessions that they turned out to be. There will be more today, of course, and another 1 or 2 tomorrow. Also yesterday we had the annual awards ceremony where NAS awards and medals were presented, which again were just stunning, very impressive, and fun to hear because of the broad sweep of science that was represented and recognized. And we heard from this year's public welfare medalist, Neil deGrasse Tyson, kind of a stirring call to arms of what the mission of the National Academy of Sciences is and the history of it. It was fun. This morning, I want to focus on some items connected with the conduct of science, reproducibility, access to data, how we evaluate science, and so on. It's going to be a recurring theme for some years, and I wanted to call your attention to some of the things that have been happening and some great progress. I should also point out for many of you who have asked, the Foucault pendulum is hanging again. So I hope you've noticed, but please don't knock it over. All of us know how to conduct research, but we don't stop and think too many times or that regularly about all that goes into it. So I want to give just a brief reminder and then push on. Science depends on curiosity, inspiration, observations, calculations, formulations of concepts, resources, communication of ideas, and data and reproducibility. Reproducibility in science, the reproducibility of scientific experiments and calculations embodies an absolutely fundamental aspect of science. As we all know, the ability to replicate experiments and to verify findings by using independent methods or by independent investigators simply repeating earlier experiments is critical to the advancement of science. This ability can be used to formally test hypotheses, or it can test particular predictions, or simply confirm observations of system variables, for example, in response to the manipulation of a variable. Efforts to reproduce experiments enable science to be self-correcting, and this quality of science is very special and very rare amongst all human endeavors. We also know that independent verifications of experimental results can guide subsequent research, for example, by solidifying previous findings. When previous results are not confirmed or strengthened, the disconfirmation can allow new ideas and hypotheses to be generated and avoid wasting of time and a number of wild goose chases if the erroneous findings had been followed. In this pursuit, it helps greatly to describe an experiment so that it can be repeated. Indeed, it is essential to describe clearly in written publications experimental methods, materials, and results so that subsequent research can be compared. Sometimes follow-up experiments occur soon, sometimes years later along with advances in experimental equipment and methodology. In all cases, the written record is essential, as is access to experimental data. This process enables science to be self-correcting. I just I don't know of any better way. I don't know if you do either. Thus, the reporting of research results itself is clearly an essential step in science's progress. If you don't report results, no one can know of what you have done. It is as if you have done nothing if you don't report. Yet, complications arise in reporting that can impede the completeness of reporting of methods, initial conditions, assumptions, characteristics of data, statistical methods, and so on. So today we have an emphasis on brevity and speed of publication. Increasing numbers of publications and of journals, some with differing standards and modes of operation, can also impede full reporting of experimental conditions and results. Additionally, various bodies now employ metrics of publication as they evaluate individuals, programs, fields, and institutions, and some metrics are acting as disincentives against rather than encouraging reproducibility in research. Today I want to discuss or increase awareness of some signs of trouble in the reproducibility of research and to identify some of the topics in which we as researchers can help to improve prospects for scientific progress, while we also increase public respect and support for science and an enterprise. A lot is going on. Some of you are at the forefront of it. I've been catching up, and over the last several months have learned a great deal. Let me start with some signs of problems. Why are we having this talk? Well, each of us can recall some instances of erroneous or irreproducible research that have become high-profile cases. For the most part, I'm not talking about those, but just to recall a few. The Lancet paper that has had a very detrimental effect on adoption of vaccination methods and encouraging resistance. I won't elaborate anymore. Of course, it's been thoroughly discounted, but it had a bad impact. A number of stem cell research claims from researchers in several countries that have turned out to be irreproducible, not reliable. A large problem some years ago in materials physics that was shown to be largely fraud. I will not elaborate any further about these specific incidents, but they get your attention, and they certainly represent cases that have angered independent experts and have aroused public attention and have led to institutional investigations. In some cases, large claims have been made that were shown to be erroneous or even fraudulent. While these kinds of cases are indeed serious, they also provide evidence that science is self-correcting. After all, how were the errors identified? That is, the mistakes and or misconduct are discovered and addressed. In fact, when large claims are made on topics of great commercial or medical or regulatory, environmental interest, competing scientists often mount experiments quickly to test the original claims, as happened, for example, with the claims of cold fusion 20 years ago now, 25 years ago. However, broader impacts of irreproducible research have been offered recently and demonstrated by individual scientists and also by mainstream newspapers. There have been a number of articles in The Economist magazine, New York Times, Washington Post, The Guardian, and others. For example, and this is a photo of a cover of Economist, and we've talked about this at a couple of our regional meetings with members, but we're learning more. For example, this Economist article from late 2013 with the inside story, which was maybe 6 pages, Trouble at the Laboratory, notes problems and practices in a variety of scientific fields, and it quotes scientists who have become aware of such problems. The article goes on to examine practices that might be contributing to errors, everything from experimental design to statistical analyses and sloppiness under pressure for results. The article's actually rather fair, well-balanced, as is a lot of their science reporting in The Economist magazine, but there was a cartoon that came with it, And it was kind of lurid, showing somebody sweeping under the rug broken laboratory glass and so forth. But for the most part, the article was balanced and informative. The Economist mentioned things like indicators of the frequency with which research cannot be replicated. There was, for example, in this same article, a highlight of a perspective that appeared in Nature magazine written by researchers from Amgen Corporation. In that perspective, several pages, they reported their attempts to confirm results from 53 notable papers in preclinical cancer research, and their attempts to replicate this research, which is how they decide where to spend their development money for prospective cancer treatments, pharmaceuticals. Their attempts to reproduce 53 selected experiments in preclinical cancer biology research succeeded in only 6 cases. And they attempted to contact authors and to learn more about what the differences might have been without much success. In that same Nature paper by Amgen researchers, they studied, and when I distribute this speech, I'll give you links to these documents. They highlighted a paper by Bayer Healthcare in Germany in which only 25% of a group of studies that they were trying to confirm could be confirmed well enough to justify continuation of research and development, mostly again in cancer biology. The Economist also reported, for example, that some experiments in the psychology using priming techniques have led to erroneous claims or at least unreproducible. Now, priming in psychological research consists, for example, of introducing a stimulus to experimental subjects in an attempt to, as an experimental method, to see how they react to statements and to accepting behavioral changes themselves. And the stimulus can be something direct or it can even be subliminal. Many of the results of priming research in psychology are weak results, so they require the appropriate statistical power to analyze them, and they've led to some difficulty in reproducibility. In a minute, I'll report on some progress. There were more such examples in the Economist article, but there are other places, as I say, to find an overview of what's happening. So how seriously should these reports be taken? Many questions arise about the frequency of the incidents, how often are they happening, and whether it's increasing. How damaging are these kinds of happenings to science itself? How much is statistical analysis involved? It's a commonly thought problem. How much misconduct or fraud is there? Are some experiments not replicating earlier results? Are they compromised by the use of poor materials or of poorly characterized experimental conditions and materials, such as in cell lines? Are inherent complexities of experiments, for example, experiments on living organisms or cells, which are very complicated, are they partly to blame? Is the haste to publish, and to publish often, causing some of this problem and going awry in other ways? Is the use of extremely large data sets, too large for anyone to be familiar with all aspects of them, leading to confusion and errors? Are multi-authored papers and multi-discipline papers more prone to slip-ups? Possibly. Are reviewers and editors overloaded? And what should be done and by whom? Let me summarize some of the responses and actions that I've begun to learn about. Some of them are quite impressive. Some of the responses that are called for are not yet happening as we seek these more powerful methods of self-correction. In some fields of science, projects are being mounted that are squarely aimed at determining the causes of difficulty in replicating findings and at improving capabilities. For example, there's a formal project underway now called the Reproducibility Project in cancer biology. It aims to conduct independent laboratory experiments to determine whether findings from prominent experiments, again in preclinical cancer biology, can be replicated. So a governing mechanism has been set up. It's being sponsored by the Laura and John Arnold Foundation, which you will hear has a serious interest in these matters. So an oversight group is created. 50 outstanding prominent experiments of the last 3 years or so are identified from published literature. Their authors are contacted. Replication experiments are then conducted by researchers in third-party laboratories, many of whom are being paid by this whole organization. It's coordinated by the Science Exchange and the Center for Open Science, which is at the University of Virginia. Another project, very different but the same general goal, the Reproducibility Project in Psychology, is going about it very differently. They aim at determining how replicable are key results from selected journal publications which they select. The project focuses on journal articles that have appeared in 3 selected psychological journals, and scientists from all over the world volunteer. That's the crowdsourced element. Scientists from all over the world volunteer to conduct experiments aimed at testing the replicability of these selected published papers. They agree to follow a structured protocol for designing and conducting these potential replication studies, and the open source software facilitates rather open collaboration and discussion of the research. This project is overseen by the Center for Open Science in Charlottesville, as I said, and it is also funded by the Laura and John Arnold Foundation. And there are other efforts, some of which have been spurred by some NAS members to deal with these potential issues of irreproducibility in psychological priming research that I mentioned earlier. Now, if you'll notice, and of course you have noticed, both of these particular projects are field-specific. It's not a magic bullet across all of science that's being undertaken here. I happen to think that's a good approach, although there are counter-arguments. For example, we issued a report in 2009. The co-chairs were Phil Sharp from MIT and also Dan Klepner from physics at MIT. And the title was Ensuring the Integrity, Accessibility, and Stewardship of Research Data in the Digital Age. They concluded that although the general principles were clear of what should be done, that actions were going to be required or are required from specific fields of science to achieve what the report promises, namely ensuring the integrity, accessibility, and stewardship of research data. They showed how different today's definitions and characters of data sets are, field by field. What are the metadata? How much, again, the characteristics of the data vary strongly. So while the principles are clear and they favor openness and transparency, accessibility and so forth, availability of data, there are so many limitations that arise field by field that they become something that has to be taken account by the experts in that field. Issues of medical privacy, of commercial and proprietary interests, of legal matters like science that's used as the basis for regulatory or trade law, things like this. So there are many issues to deal with field by field. So I rather like this field-specific approach to get started. Let me mention another set of major projects which is underway. One of them started in 1995 by our own NAS member colleague Gary King, a quantitative political scientist. He launched a political science-specific replicability project in 1995. He called it Replication. It's aimed at improving the norms of data sharing and replication in scholarly political science research. He has called for and helped to formulate new standards and protocols and software for citing, sharing, analyzing, data, along with its archiving, preserving, distributing, cataloging, a lot of attention to data. And it has led, in many cases, to the creation of data repositories, where extensive data sets are being stewarded and made available to anybody years later on different areas of research. King also launched a project called Publication. This one is aimed largely at students, and these courses are now being taught all over the U.S. on the methods that he's developed with a couple of other colleagues on what can a student learn from generalizing in this field and how to write papers, so that each one of them is being asked to take on a replication study, and they are virtually guaranteed a publication out of it themselves if the work is done right. So there's a real incentive. This has now morphed into a third project that King and his colleagues have created called the Dataverse Network, and they now have nodes and data repositories in a number of scientific fields, not just the quantitative social sciences, but into the physical sciences as well, with nodes on various campuses. You can look up some of these terms. It's really impressive. So there's a lot of progress underway. Different fields of science may have differing views of how serious all of these questions are in the first place, and let alone how to deal with them. Here at the National Academy of Sciences and the National Research Council, we're undertaking some of these questions too. For example, the Division on Behavioral and Social Sciences and Education is beginning a project on research replicability in the behavioral and social sciences, once again sponsored by this Arnold Foundation, that looks very interesting. Our Committee on Applied and Theoretical Statistics, which is under the Standing Board on Mathematical Sciences and their Applications, has recently convened a 2.5-day workshop to explore whether improved statistical methods or improved application of existing methods could increase the reproducibility of research. They've asked questions like the following. It was a really interesting symposium with quantitative people from many fields. Some of the questions were, how can we quantify the reproducibility of scientific results? How close can you expect to get? The variability across studies is expected, of course, so how can we assess the acceptable degree of variability, and when should we be concerned about reproducibility? How can the choice of statistical methods for designing a study and analyzing its output data affect the reproducibility of the result itself? Are there analytical approaches that can enhance reproducibility within disciplines and overall? Or do we need conceptual, theoretical frameworks that are new for assessing the strength of science from studies? Specific actions are also being taken in other quarters to improve the statistical treatment of research data. Just focusing on statistics for a minute. Our NAS member, Marcia McNutt, who of course is the editor-in-chief of Science Magazine, published an editorial called Raising the Bar, and I have not printed the text because you couldn't read it. But the gist of it is, in an attempt to improve the statistical treatment across many scientific fields in Science Magazine, they've established something called the Statistical Board of Reviewing Editors, parallel with their Board of Reviewing Editors in general. This group of experts will contribute to the review of manuscripts submitted to science and will evaluate data analysis methods and their application to interpretations, to measures of statistical uncertainty, and therefore to reproducibility. And of course, there are broader issues, not just statistics, that surround research reproducibility, and they are also being considered by journals. Again, I'll refer to an editorial that Marcia McNutt wrote, Journals Unite for Reproducibility, where she describes briefly that a group of editors from over 30 journals met last year, and they discussed principles and guidelines to increase transparency and reproducibility, for example, in preclinical biomedical research. The principles, which are of course important, have already been adopted by a number of journals. They focus on statistical methods, experimental design and details, accessibility to data and to experimental materials. The guidelines, on the other hand, deal with best practices for image-based data and experimental description, including fuller specifications on laboratory animals and cell lines. The journal eLife, which Randy Sheckman now edits, has arranged in a separate effort to review some cancer biology project proposals, that first field-specific method project that I mentioned. So eLife has arranged to participate and help in that effort by reviewing some of the project proposals for replicability that come in, or so-called registered reports, for many of those same top 50 cancer biology papers that had already been selected for the project. And eLife has already published several of these project proposals after peer review. The groups whose reports were published in eLife are now engaged in efforts to reproduce these key experiments from those papers that had already been selected. So we really do look forward to hearing how this goes. Of course, this whole variety of examples that I'm giving is occurring in response to identified cases of non-replicable research, or simply in efforts to continuously improve how science functions, how it self-corrects. But there are other potential reasons why we have to pay attention to this. For example, to fend off top-down edicts, for example, from governments. Recently, and I mean recently, one committee of Congress right now is discussing a call to demand that NSF support a study here at the Academy to, quote, assess research and data reproducibility and replicability issues in interdisciplinary research, and to make recommendations on how to improve rigor and transparency in scientific research. So we haven't received that request yet because it hasn't come all the way through the particular House of Congress, but we'll be watching. Let me speak for a few minutes about the conducting and reporting and evaluation of research. Clearly, being an active researcher is a privilege today and always, and it's very enjoyable. Making discoveries is just so rewarding and fascinating. We heard some nice examples in the award ceremony on Sunday, of course. Watching and understanding the advances that other people are making is also very stimulating, as it is to sense the potential applications of these discoveries. And it's true, frontiers of understanding are being extended today in ways that were really unforeseen in earlier ages. And additional progress is easy to imagine coming out of these breakthroughs today. And of course, scientific competition is a powerful force that helps to drive this entire realm of progress. And moreover, this scientific research enables better teaching too. For example, by involving undergraduate and graduate students, along with postdoctoral fellows and other senior researchers, where they can emphasize scientific ways of thinking as the communication is extended. So educational benefit also arises by this involvement, and inviting school teachers into research projects at university and government laboratories. So it's a wonderful enterprise. But nonetheless, there are some patterns in research today that cause concern, and we have to address those ones, especially those ones where we have some control. If one is speaking about the federal budget for one of our research agencies, NIH or Department of Energy or something, there's not much we can do. But some of the practices that I'm summarizing quickly today are susceptible to our influence. In fact, we created some of the processes that need to be adjusted. The overall growth of science worldwide, which is a positive development, has also led to many more journals of variable quality and to more disciplines with differing practices. The complexity of many scientific questions has led to the creation of large research groups and the need for support staff and more equipment. Competition for research support has become more strained, and there is a perception of hyper-competition, in the words of 4 of our members who convened a special session last year to discuss this perceived crisis in biomedical research, largely due to this hyper-competition. And in some ways, it does lead to a deterioration in how science is conducted, with the example I just gave. The reporting of research results, essential as it is, has become burdened by many excesses. Generally, there is this pressure to publish more often and to publish briefer papers quickly. The need to demonstrate the impact of one's research is often manifested by citing numbers of papers. Large collaborations with multiple authors, often in other countries, make it more difficult to report results in ways that encourage replication and independent verification. The desirability of publishing in the most selective journals, which tend to favor papers that report something really new and differently, has simultaneously diminished the rewards of confirming and/or testing previously published papers, the self-correction mechanism. Well, what happens when errors are published? Ideally, journals publish retractions of individual papers when errors are identified. In cases where researchers find their own mistakes and publish a retraction, science is well served and the researchers are even more respected, the people who reported it. Science also benefits when other researchers publish independent corrections. Yet, there are cases where authors refuse to retract, even when their co-authors are willing to retract. And some of these cases, it's true that neither the journals nor the researchers' home institutions have the ability to conduct inquiries. Indeed, the embarrassment and stigma of retractions are disincentives for institutions to pursue inquiries as to retractions or even to investigate misconduct. Earlier this year, we had a retreat sponsored by the National Academy of Sciences and the Annenberg Foundation. And I certainly learned a lot. And at that retreat, it was suggested that there's a need for 2 different kinds of retractions. One could be called voluntary, in the former case that I use an example of. The former case, that one, voluntary, would be seen as a positive contribution, and the second case, which might be called for-cause retractions, perhaps forced, would be viewed much more negatively. So there's work to be done with retractions, and it turns out that journal editors don't have all the authority that I thought that they would have. In most fields, we also have to sort out rules for co-authorship of research publications. It's really hard to state what rules we're using. Guidelines on how to decide co-authorship vary greatly by discipline. At one time in my career, I had an operational rule that to be a co-author of any paper, that person had to understand everything that was in the paper. And I used that rule for some time, and I find it impossible to use it now. We depend on so many complicated data sets as input, experimental materials, experimental practices, instrumentation, computational methods that someone else has developed. And it's very unlikely that many people as individuals understand everything in the paper. You can think about the ridiculous or the hardest examples of hundreds of authors, but anyhow, that rule is too simple. We have to sort out what our rules for co-authorship are. These new large data sets themselves are gathered by specialized instruments, and the complex calculations can probably not be understood and described well by every co-author in some cases. So being generous with co-authorship is a good rule, but it can also compromise efforts to report so as to facilitate replicability and this ability to self-correct. Authorship as a courtesy to senior investigators can also be discouraging to other contributors and can impede replicability. This ghost authorship or courtesy authorship is something we should minimize for sure. The many issues of authorship and of credit and responsibility for publications, credit and responsibility, need re-examination, probably again inside individual research disciplines, where the culture of publishing and reporting differs from field to field in many cases. Evaluations of individual researchers, as in hiring and career advancement, are highly important functions, and they involve issues related to publications in research institutions. Many individuals have noticed that citation data for individuals and for journals themselves are being used indiscriminately, giving at least the appearance of replacing more fundamental measures of quality. Selected citation data are useful if they're used appropriately, but we must choose them carefully. Workloads of editors, reviewers, and of academic advancement committees are heavy, but we must insist that the evaluators read papers, read reports to evaluate the quality and to reject these cavalier citation data, which are often generated by machine, never touched by human hands, and have many decimal points. I just made that up, but it's true. There was a notable declaration about a year ago, the San Francisco Declaration on Research Assessment. It stemmed mostly from cell biologists. In fact, I saw Carol Greider this morning, a cell biologist, and it's a strong statement about the overuse and misuse of citation data to evaluate people, projects, institutions, journals, and they made a very good point. I'll have a reference to that in the written version of this speech. So signs of progress in this direction towards self-correction, can be seen in some evaluation processes that do limit the number of publications that may be considered or submitted. For example, nomination for membership in the National Academy of Sciences. For some time, we've limited that nomination to 12 papers, no more. In fact, it's quite exciting to see a nomination that maybe only lists 6 papers. There must really be something good there. Funding proposals to the National Science Foundation and National Institutes of Health require focus on a selected number of research publications, not a long list, not an emphasis on numbers of publications, numbers of citations. So that's encouraging. But we need similar progress in many other venues. For example, in academic advancement procedures at research universities. I was bugging one of my colleagues at one of our top research universities about some of their procedures using citations and counting papers literally. And he told me, well, the dean makes them do it. No way. The faculty control these things. The faculty control the criteria. And any dean who's insisting need not remain dean for very long. So what's next? So what's next? In preparing this little summary of issues about replicability of research and of ongoing efforts to improve the prospects for replicability, I've learned a lot. There's a lot of good going on, good work underway. Yet there's still a lot to do, and the Academy itself has to do more. There's some ways where we really can help. For example, we can convene groups to learn what's going on, what's working in individual fields and journals. We can work with the scientific societies who publish some of those journals. We can also eventually provide guidelines towards best practices for data sharing and access to experimental materials. PNAS has had that process in place for a long time. It's not fail-safe, but the principles and the instructions are quite clear and strong. So I'm very encouraged by these reproducibility projects that I mentioned today, the cancer biology one, the psychology one, the 3 projects of Gary King on data sharing, the projects on the focus on statistics, some of the journal actions. So what do we do now? Well, we should be evaluating the results of those particular experiments and see if we can detect improvement and how to do it efficiently without being too burdensome. And in all of these efforts, there are roles for individual researchers, for university and government lab leaders, for journal editors and reviewers and disciplinary scientific societies, and wherever career advancement and research awards are decided. There are also major incentives for us all, strengthening the ability of science and individual scientists to make progress and to continue to command respect from the general public. And I hope that each one of us will pitch in to help to assure this self-correcting aspect of science through replicability, reproducibility. I'm not sure which one is easier to say. And of course, access to relevant data. The important related issues of research publications and of evaluation of research also need our continuing attention. In all of these topics also, there are some very talented and interested journalists who cover scientists, who are helping to sense public interests and who can give us aid to address these questions. In fact, one of them is giving a talk here tomorrow, Professor Kathleen Hall-Jameson, who helped to convene our Annenberg retreat. She has a serious interest in research reproducibility, and she understands the process of science. And she represents a class of journalists and communicators who know that they have a role in helping the public to understand what we're doing, what it means when advice on a dietary requirement changes from month to month, how the process is aimed at converging and things like that. So work with them if they give you the chance to do that. Separately, tomorrow, Tuesday, I think it's April 28th, there will be a breakout session here in our lecture room led by Randy Sheckman, focused exactly on some of these topics. At the Academy, we will work and continue to improve our efforts, and we will issue reports as we proceed. There's an upcoming report from our Committee on Science, Engineering, Public Policy, COSAPOP, which is chaired by Dick Zayer. The particular report was led by Bob Neerum, Georgia Tech, who's an biomedical engineer, which is also focused on replicability and on data access and integrity in science. And we will issue pretty soon a brief summary of this NAS Annenberg retreat involving the members of that group. So I look forward to seeing a lot more encouraging progress towards, my handwritten note's tough here, towards sharpening the ability of science to be self-correcting. I think we're on the right track. But do remember that lurid cartoon from The Economist, because that is the way some people see the enterprise. Let's continue and ever forward. Thank you.